Number 6. So our last static equilibrium problem, we're going to start by drawing a free body diagram. There's my ladder over here, and the wall and the floor. So we have a person here, so his weight is going to push down on the ladder here, and then the ladder itself will have some weight, and we're going to assume it's a uniform ladder, so it will be at the center. And then over here we'll have a normal force and a friction force, which will go to the left because the ladder would slip to the right, so the friction opposes that motion. With the wall here, the ladder would slip down, so we have a friction force upward. No, sorry, we don't have a friction force. It says that the wall is frictionless. If there was friction, it would go up, but we have a normal force. So we're looking for the coefficient of static friction, which has to do with this friction force here. So we can pick our pivot point to be over here since we don't care about this normal force. So go ahead and label our forces F1, F2, F3, and F4. Now, with an object that's diagonal, I think that it's easier to use the definition of torque, that is F times D, instead of F perpendicular R. So let's go ahead and find our D's here. So to find the D, what you're going to do is you're going to extend that force line. Now I'm going to move this one out of the way since we don't care about this force, it doesn't produce any torque. You're going to extend this force line here, and then you want the distance from the pivot to that force line. So this right here, from here to here, that would be D1. And we know what that is here. The ladder is 12 meters long, so this is going to be 4.1 meters over here, 4.2 meters, sorry. And D1 is going to be cosine because it's the adjacent side here, and this angle here is the same as this one. So it's going to be 4.2 cosine of our angle. F2, do the same thing. Extend that force line and draw a line from the pivot to that force line. So from here to here, that's going to be D2 over here. And this was the weight, so it was halfway. So this distance from here to here was 6 meters. So this is again going to use the cosine of that. So it's going to be 6 cosine of the angle. For F3, we're going to extend that force line. Just extend it straight here. And then we want a line from the pivot to this force line. So from here to here is going to be D3. Now we know this angle over here, and we know the length of the ladder. So D3 is opposite. The length of the ladder is 12 meters, so it's going to be 12 sine of theta. And for number 4 here, we extend this force line. And D4 is going to be from the pivot point to that force line, so it's going to be this whole distance here. So from here to here is going to be D4. So that's going to be the same as the distance right here, which is adjacent to the angle. So it's going to use cosine, 12 cosine of theta. And now we just need to define our forces. F1 is the weight of the person, 874 newtons. F2 is the weight of the ladder, which is 400 newtons. Now, unfortunately, we don't know F3 or F4. We're looking for something that has to do with F3. Now, what we can do on the side here is look at the sum of the forces in the y direction equal to 0. And if we just look at the y forces, we only have 3 forces in the y direction, because the force that was here, that was in the x direction. So we know that F4 is positive and F1 and F2 are negative. Those must sum up to 0. So we know that F4 is equal to F1 plus F2. So it's going to be 1274 newtons. So I'll go ahead and write that down. And now we only have one unknown, which is F3. So we can go back to this and sum up our torques equal to 0. So F1 is going to produce a clockwise torque about this pivot point here. So negative F1d1, F2 as well, negative F2d2. F3 will also produce a clockwise torque. It's pulling it here this way. So minus F3d3. F4 will produce a counterclockwise torque plus F4d4. All of these torques will sum up to 0. And now we can solve for F3. So F3 will be minus F1d1 minus F2d2 plus F4d4 divided by d3. Don't have a calculator with me, but I'll let you plug in all the numbers. We have everything defined. And now the last step is to figure out the coefficient of friction. F3 here is the friction force. So the last step, well, we know that the friction force, which we usually call Fs here, is equal to mu times n. And n was the normal force, which was F4. So it's equal to mu times F4. And now we can find mu, which is what we're looking for, is just going to be F3 divided by F4. And you should get 0.49 for that coefficient of friction.